Okay, so I don't know what was the last that you have heard. The last that I said was that when we apply the y-z mirror plane, then that leaves the y and the z coordinates unchanged because they are part of the y-z mirror plane, but the x coordinate changes its direction. Okay. What does that mean now for the matrix representations representing the symmetry operation? Well, it means that our new coordinates, x prime, y prime, z prime, what is now happening then? Wait a moment. Yeah, I think we're good. X prime, y times z prime are being transferred into the coordinates minus x, y, and z. So now the matrix that correctly transforms the old coordinates x, y, and z into the new coordinates minus x, y, and z is this one here. So it's minus 1, 0, 0, 0, 1, 0, and 1, 0, 0, 1. And we could again show by applying the multiplication rules for matrices that this is the correct transformation matrix. Okay, so let us quickly do this. So minus 1 times x plus 0 times y plus 0 times z, well, that just gives minus x. 0 times x plus 1 times y plus 0 times z, well, that gives just y. And 0 times x plus 0 times y plus 1 times z, well, that gives just z. So again, we have shown that this matrix here is the correct transformation matrix for the symmetry operation sigma yz. Okay, last but not least, we should not forget about the identity, which is also present. So for the identity, the correct transformation matrix is the following form: 1, 0, 0, 0, 1, 0, and 0, 0, 1. So now we have identified all the matrix representations of all the symmetry operations in the point group C2V. Okay. So now here's an overview over them. Okay, so this is the one for the identity. This is the one for C2. This is the one for sigma yz. And this is the one for sigma xz. So now when you analyze these matrices, you see that they have all a fairly similar form. Okay, you see only non-integers here on these diagonals of these matrices, which are also called the traces of these matrices. Okay? All other values are being 0. Okay, so for that reason, you can say now that these characters here, 1, minus 1, minus 1, and 1, they tell you what the symmetry operations do with the x coordinate. Okay, so these 4 characters here, they tell you what the 4 symmetry operations do with the y coordinate. And the last 4 numbers here tell you what the symmetry operations do with the y coordinate. Okay, so now each row of numbers are called a so-called irreducible representation. And these numbers here are called so-called characters of the irreducible representation. So this set of characters here would be the irreducible representation for the coordinate x. This set of characters here would be the irreducible representation for the coordinate y. And these four characters here would be the irreducible representation for the coordinate z. Now, irreducible representations mathematically can be added, and the addition of two or more irreducible representations gives what in group theory is called reducible representation. Okay, so if we add all these characters up here, then that gives a reducible representation, which is the form 3, which is just 1 plus 1 plus 1, minus 1, which is minus 1 plus minus 1 plus 1, 1, which is minus 1 plus 1 plus 1, and 1, which is 1 plus minus 1 plus 1. Okay? Okay. Yeah, these are just reduced representations for the y and z characters, and the numbers tell you basically whether the algebraic sign of the coordinate is being changed. If it's minus 1, and if it's not changed, then the character is being plus 1. All right, so this is here called the reducible representation. All right, so now in group theory, certain combinations of characters in the irreducible representation are being assigned a so-called symmetry type. So for instance, this irreducible representation here has the so-called symmetry type B1. This one here is the symmetry type B2, and this one here for the z coordinate has the symmetry type A1. So I wanted to briefly explain how one can understand these symmetry types. So B means that we have an anti-symmetric situation with regard to the rotation about the principal axis. Okay, so now in this case, our principal axis is C2. So anti-symmetric means that the algebraic sign changes. So therefore, all irreducible representations which have a character -1 are B-type. Okay, so this is the first one for the x-coordinate, the second one for the b-coordinate, but not the third one for the z-coordinate. Okay. Okay, so now the subscript 1 means the representation is symmetric to a C2 perpendicular to the principal axis, or if lacking, to a vertical mirror plane V, sigma V. So now in this case, we do not have C2 is perpendicular to the principal axis, but we have a sigma V. Okay. So the sigma V is this one. This one here would be the sigma V prime, and you see that for these two irreducible representations in the first and the third row, the characters are 1, so we have a symmetric situation. So we get a subscript 1. Okay, if the situation is asymmetric, then subscript is 2. Okay, so subscript 2 means that the representation is antisymmetric to C2 perpendicular to the principal axis, or lacking to a vertical sigma V mirror plane. Okay. So A, as I just said before, means symmetric with regard to rotation about the principal axis, which is here, the C2. Yeah. All right. Then irreducible representations can be used to determine the symmetry of an orbital in a particular point group. And as we'll see later on, this is very useful in order to understand molecular orbital theory using group theory. So for instance, when we have an H2O molecule, then we can put ourselves on the oxygen, and the oxygen has a 2s orbital. So now, what would be the symmetry of this orbital in the point group C2V? Okay. So in order to determine this, we would need to see what the symmetry operations would do with this particular orbital. So if we carry out the symmetry operation E, will this orbital be changed in any way? The answer is no, so the character is 1. If we carry out the C2 symmetry operation, this will leave this orbital unchanged, so the character is 1. If we carry out the sigma V symmetry operation, this orbital won't be changed. And if we carry out the sigma YZ symmetry operation, then this orbital also won't be changed. So that means that the symmetry type of this orbital will be A1, represented by these 4 characters, 1 in the irreducible representation of the type A1. So now we can do the same for the 2pz orbital. So now if we carry out the symmetry operation E, does that change the 2pz orbital in any way? The answer is no. If we carry out the C2 symmetry operation, there also won't be a change. If you carry out the sigma xc symmetry operation, there won't be a change. And if you carry out the sigma yz symmetry operation, there also won't be a change. So the symmetry type of the pz orbital in the point group C2V is also A1. So now, what about the xc? Okay, so it's the px orbital. So the px orbital points this way. So as we carry out the symmetry operation E, well, certainly nothing will change to this orbital. But now if we carry out the symmetry operation C2, yeah, you will see that this will flip the algebraic sign of the wave function, because the blue lobe will be moved into this position and the orange lobe will be moved into the position of the blue lobe. So the algebraic sign of the wave function changes, and that's associated with the character of -1 in the character table. Okay, so for that reason, we would expect that the 2px orbital is of B type. Okay, now it could be B1 and or B2, and we'd need to see, well, as we carry out the sigma xy symmetry operation, does the algebraic sign of the wave function change or not? Can you see this? Does it change or not? So we are mirroring.
No.
Yeah, we're correct. Yeah, so we're mirroring at xc, which is in the plane of the molecule. So the orange lobe stays the orange lobe, and the blue lobe stays the blue lobe. Okay, and that means that our symmetry is B1. Okay? Because here the character is 1. So last but not least, also let's look at the py orbital. So the py orbital stands perpendicular to this molecule. So as we apply the identity, certainly our py orbital won't change in any way. So as we carry out the C2 symmetry operation, we see that, well, the orange lobe will rotate to the back, and the blue lobe will rotate to the front. And that means that our orbital does change the algebraic sign. So that means that we will again expect B-type symmetry. So now we still need to discriminate between B1 and B2. So in order to decide this, we next look at the sigma xc operation. So in this case, does the algebraic sign of the wave function get flipped or not? What do you think?
Yes, it gets flipped.
Yeah, it gets flipped, correct. So that means that the symmetry type in this case is B2. Okay, I see our time is over. Let's stop at this point and let's expand on the idea of determining symmetry types of orbitals and molecules that belong to a particular point group. In the next class, so I just stop the recording again.